If you want an AI to extract human emotion in the real world, you have to accept that the real world is chaotic. Voices overlap, cameras shake, backgrounds are filled with slamming doors and traffic. Compare that sensory noise to the transcript of the exact same conversation. The transcripted text is perfectly clean. The words are stable, unambiguous data points. Look at this visualization of the 3 data streams. Up top, the text modality is built from solid, discrete blocks of dense emotional meaning. Below it, the audio and video streams are continuous, erratic waveforms, heavily corrupted by random spikes of environmental static. The emotional cues in these lower streams are incredibly sparse. Historically, multimodal conversation emotion recognition models, or EMSRs, have ignored this structural difference. They use what we call flat fusion. As you can see here, all 3 streams route symmetrically into a single concatenation node. When they do, the jagged static from the audio and video waveforms bleeds directly into the clean text blocks, which triggers a massive error in the final output. By treating all modalities as equal partners, the neural network grants them equal influence. A transient burst of audio noise, like a passing siren, is assigned the same mathematical weight as the actual spoken words, corrupting the semantic integrity of the entire sequence. This implicit weighting creates severe information distortion. Because of this exact problem, highly complex multimodal models will sometimes yield worse emotion prediction scores than a simple model analyzing the text alone. To accurately extract emotion from real-world data, the architecture has to reflect reality. A model cannot treat all inputs symmetrically. It must abandon flat fusion and explicitly anchor its architecture to the most reliable signal in the room. Researchers have proposed a new pipeline designed around a strict hierarchy. Instead of welcoming all data equally, this model forces audio and video signals to mathematically prove their relevance before they are permitted to merge with the text stream. This diagram maps the new architecture. Raw data enters on the left and moves through 3 sequential processing bottlenecks. First, a differential denoising block applied exclusively to the audio and video. Second, a graph contextualization stage that connects all 3 modalities. And finally, a text-guided diffusion process that executes a strictly unidirectional merge. The entire system relies on structural asymmetry. It treats the text stream as the absolute, unquestionable anchor modality. By explicitly controlling how gradients and signals route between these unequal streams, the pipeline prevents transient noise from degrading the overall prediction accuracy. The first major hurdle in this pipeline is processing the audio and video. The model has to separate actual emotional cues, like a sudden frown or a heavy sigh, from the surrounding environmental noise. Standard self-attention mechanisms struggle here. If a camera glitches or a door slams loudly, a standard attention mechanism will often assign a massive, high mathematical weight to that distraction, simply because it is prominent. The architectural solution to this is a highly specialized component called the Differential Transformer. Think of its function like phase cancellation in acoustics. When 2 identical, opposing waveforms meet, they cancel each other out, leaving a perfectly smooth surface. The differential transformer takes noisy input and generates 2 distinct attention maps side by side. Both contain true signal hotspots surrounded by scattered static. The model mathematically subtracts one map from the other. The random static cancels to 0, leaving only the persistent hotspots illuminated. Through this mathematical subtraction, time-irrelevant noise is suppressed by destructive interference. The data points that survive this process represent temporally consistent information. These are the sustained facial expressions and consistent vocal tones that actually carry human emotion. This differential denoising step acts as a critical gatekeeper. It ensures that only clean, highly relevant audio and visual features are allowed to progress deeper into the neural network. Isolating clean signals solves only half the problem. Even a perfectly clear audio recording of a sigh or a sharp video of a smile is largely meaningless if analyzed in total isolation. Human emotion in a conversation is reactive. It depends entirely on context. An emotional reaction is defined by exactly what was just said, and specifically who said it. To build that context, the model introduces its second architectural component, modality-specific and cross-modality relational graphs. Look at this timeline. The model maps intramodal dependencies, drawing an edge from speaker A's first vocal tone to their second. Simultaneously, it maps intermodal dependencies. Dotted lines connect speaker A's text directly to speaker B's video nodes, mapping precise reactive emotional shifts. During training, backpropagation travels along these precise graph edges. This forces the network to learn speaker-dependent emotional dependencies across the entire conversational timeline. These relational subgraphs transform isolated feature tensors into a dynamic, structurally aware map of the conversation, priming the data for the final fusion phase. Now we reach the final and most critical bottleneck, fusing these interconnected graphs back together to make a final emotional prediction. To understand this step, we have to contrast it with the baseline technology, which typically relies on standard multi-head cross-attention. Standard cross-attention allows information to flow bidirectionally between modalities. This forces clean text streams to adapt to sparse, erratic audio and video inputs. It creates intense analytical turbulence, diluting the most reliable data. To solve this, the paper introduces a unidirectional solution, a text-guided diffusion mechanism. The text modality acts as a central carrier wave, with audio and video as smaller secondary tributaries. The text stream sends targeted pulses to these tributaries. When a pulse hits, specific audiovisual data packets break off and merge smoothly into the central text flow. This mechanism adaptively diffuses audiovisual information into the textual stream, but strictly on the text terms. It only pulls in external data where the text specifically demands it to complete emotional context. This structure guarantees semantic alignment. The model actively pulls supporting evidence from the audio and video streams, rather than having arbitrary data force its way into the calculation. This unidirectional diffusion ensures a far more robust fusion. It protects the semantic integrity of the text while successfully leveraging the crucial emotional context hidden within the audio and video. Let's review the complete tensor journey from raw signal to final classification. Raw data enters the system. The audio and video route through the differential denoising block. All three modalities are mapped into a relational graph web. They converge at the text-guided diffusion node and generate a highly confident emotion class output. Differential attention acts as the gatekeeper. Relational graphs build the temporal context. Text-guided diffusion enforces the modality hierarchy. In practical applications, this architecture demonstrates extreme resilience. It is highly effective in noisy, real-world deployments like automated call centers or unstable live video feeds. However, the model's primary vulnerability stems directly from this same reliance on structural asymmetry. Because text is the absolute anchor, the entire model is completely dependent on the upstream automatic speech recognition, or ASR module. If you look at the right side of this diagnostic display, you can see the fatal flaw. Even with a perfectly clean video feed, if the text transcript is garbled, the system fails. If the ASR module outputs nonsense, the central carrier wave is corrupted. Without a reliable text stream to generate accurate queries, the entire diffusion process collapses. By explicitly anchoring its logic to the text modality, the model inherently inherits the fragility of the text extractor itself. Despite this dependency, the architecture proves a vital point in multimodal AI. Treating all data streams as symmetrical equals is a computational trap. True robustness in chaotic environments is achieved through architectural asymmetry, guided unwaveringly by the single most reliable signal.